Hey there, from Kwame Station again, a mathematics enthusiast and a teacher of Michelle Come 2 JHS of the subject mathematics in the Pung Katamansu Metro. Today, what do I have for you? We have always been doing long division such that when we get to a point, we are always asked to bring a decimal point and attach zeros to the remainders inexhaustively. Yeah. Why do we do that? Why do we do that? Why is it that when we get to a point when we have exhausted each digit of the dividend and we still have a remainder, we bring out the decimal point and then we continue the process by attaching zero to the remainders inexhaustively? Why do we do that? Follow me as I take you through the journey as well. Now, let's take an example. What I'm trying to say, let me demonstrate it. Let's say I have 4 divided by 516. Let me take a very easy one. 5161. Okay. So we'll do a long division. 4 into the first digit, 5, 4, 1, 4. Remainder of 1. Next digit, 11. 4 into 11, 2. 4, 2, 8. Remainder of 3. Next digit, 6. 4 into 36 is 9. 4, 9, 36. Remainder of 0. Next digit is 1. 4 into 1, is 0. 4, 0 is 0. We have remainder of 1. And all the digits of the dividend has been exhausted. Then here we are being taught that you bring your decimal point here, then you add 0 to this. 4 into 10, 2. 4, 2, 8. Remainder of 2. Here we are being taught, or we're being taught that because of this decimal point, you can still add 1 0 to this. So making it 20, 4 into 20 is 5, 4, 5, 20. The problem is, why do we do this? That is where I want to take you to. Journey with me as we see why we do this. So I have 5, 1, 6, 1 divided by 4. Understand that every number has a decimal point, and we know that the numbers that we do not write their decimal points have their decimal points behind the last digit. So this number is seen as 5161 point is here, and that means that we can have an inexhaustive number of zeros at the end of this. An inexhaustive number of zeros behind decimal point. It doesn't change the value of 5161. So in actual sense, whatever question you are solving is seen as such. So let's go through this. 4 into 5, 1. 4, 1, 4. Remainder of 1. After the next digit is 1. 4 into 11, 2. 4, 2, 8. Remainder of 3. Next digit 6. 4 into 36, 9. 4, 9, 36. Remainder of 0. Next digit 1 attached. 4 into 1 is 0. 4, 0 is 0. So we have 1 minus 0, 1. We are done with the whole number part. We are now in the decimal part. Once we have decimal point here, we know that every answer we get after this is after our decimal point, or it's a solution to numbers beyond our decimal point, and therefore we have to indicate it at the quotient side of our answer. So now this is what like 1.0. Because I have my point here, it's fine. I'm good to go. So 4 into 1.0, I know it is not going to be anything 1. It will be less than 1. It will be in a decimal form. So that is why my decimal point is there. So I can picture this as 10. 4 into 10 is 2. So this means that 4 into 1.0 is 0.2. If you multiply 0.2 by 4, you're going to have 0.8. So there is a remainder of 0.2, right? And the next digit is 0, the second 0 here. I bring it down, 0.20. And if I'm looking at 0.20, 4 into 0.20, 4 into 0 will be 0, 4 into 2 will be 0, and then 4 into, there'll be a remainder of 2, making 20. 4 there is 5. So you just ignore all of these and work around 4 into 20, which is 5 here. So 4 times, this answer is 0. What the 2 is 0. So 0.05 times 4. And that should be 0.05 times 4. 5 is 20. 0 is 0. 2. 0 is 0. That's 0.20 like we have here. So 0.20. This is the actual reason why we bring our decimal point to the quotient side. This is the actual reason. But in actual sense, if you are solving it, you only picture this as 10, making it easier for you. 4 into 10 is 2, 8, remainder 2, add 0, 4 into 20 is 5. Because you have your decimal point already pictured in the answer or the quotient form. Thank you very much for watching this video. We'll come your way again with more exciting videos. Until then,